Hello everybody and welcome. Today we're going to be looking at an implementation of 2D collision that you could use in your game or your simulation, anything you want really. And we're going to be doing this in Python. It's using a library called Pygame for the graphics. Not important. You can do this in any language using any graphics library, but if you're familiar with this, that helps. And so basically here it is. We've got this ball and a line here. This could be your wall in your game, right? And the ball falls right through the wall, and we want to fix that. We want to make it so that the ball like bounces off of it or slides along it, something like that to fix it. So before we get right into coding it up, first we're going to go over sort of the basic structure of how my code is set up, and then maybe figure out what you need to put into yours. So here, this main is just the runner, but what we got here is we have a vector class. This is really important. We need to have some sort of representation of a vector, and you need to be able to add the vectors together, subtract them, multiply, divide them, normalization, and also this dot product. We need the dot product. If you're using a regular math library, these functions are probably already in it. But if you're making it yourself, make sure that you have all this functionality. And we also have, and from that vector, we have a wall, which is 2 points. So the wall is 2 points, and these are just represented as vectors in some coordinate system, right? And so a wall has a 0.1 and a 0.2. And let me get rid of that. Wall is a 0.1 and a 0.2, which are just vectors. And we also have our ball, which is our circle that's going to be colliding with the wall. And so the ball has a radius, and it has a position. The position is a vector, radius is float int, whatever you want it to be, right? And it also has a velocity. That's also important. Those are the really important components of this. And everything else, this is all just for drawing it and stuff. Drawing it's not important. That's how you get it done yourself. But let's get right into it. So the problem here is our ball is being affected by gravity, and then we're updating its position. And so then when we run it, it's being updated by gravity, so it's falling. So after it's been updated by gravity, we want it to collide. So let's figure out how do we build the collision. And the way we're going to do this, this is going to be part of the wall class, or somewhere you're going to have a representation of your walls in your game, right? We're going to need to edit the wall here. So just like in the video about the math, we're going to need two vectors here. And these vectors, they actually live on the points themselves, and they point towards the center. So in order to get vectors that point towards the center, we first need to get the center of the wall. So this is center right here. And the center is just the average of these 2 points. It's the middle of the wall. And so in order to get the center, we're going to create a center, and this is going to be the average of the 2 points. So that's the sum of them divided by 2. And that's going to be our center of our wall here. It's going to be 0.1 plus 0.2 divided by 2. And now we need to get these vectors. So these vectors, they should be unit vectors. Actually, it doesn't matter if they're unit vectors, but it's just good practice to have your vectors normalized. And if you're doing this upon creation, it's not going to give you very much overhead, because it's not going to affect your runtime, right? So first of all, we need to get a vector that points in this direction. So what we can do is we just grab the vector from the center to 0.1, which is center minus 0.1. So we want to find this vector. So P1 plus this vector gets us to the center. Let's call this vec. This is vec equals center. And that's not an E, but you get the idea. P1 plus vec equals center. So vec is equal to center minus P1. So now let's implement that here. So self dot, and then we'll call this vec for now, but but we're gonna have another one, so we should think of a more descriptive name, right? So maybe let's call it center. So it corresponds to P1, so maybe center vec1. It doesn't really matter what the name is, right? So we'll just call it center vec1, and then so this is gonna be, its vec is equal to center minus P1. So it's equal to self dot center minus P1. There we go. Now we also need to grab the one from the other side, and we can use the same logic. And if this is P2, then we're going to get vec2, right? So vec2 is going to be center minus P2. So self.center center vec2 is equal to center minus P2. Great. Now we just need to normalize these. And so however you normalize them using your math library, the way I've coded it up is the vector has a normalized function which just divides the vector by its length. So we're just going to do self.center vec1 is equal to normalize self.center vec1. There we go. And then we got same thing for center vec2 equal to normalize self.center vec2. There we go. Now these 4 lines of codes, these are building our center vecs. Right here. Now we got our 2 vectors that point outwards from the middle. Great. The next thing we need to do is we need to construct a normal vector that comes out of here effectively, right? This vector is going to point perpendicular to the wall itself. And so this is going to require a little bit of finesse. So how do we build a vector that's perpendicular to this one? Well, we can represent the wall, the points from P1 to P2 as its own vector. So we just have a vector. Let's call it, what should we call this one? It actually doesn't really matter. But so this one is P2 minus P1, right? This gets us from over here to here. And we want to rotate this vector, rotate it so that it's pointing 90 degrees away from where it originally was, right? This is, now it's going to be pointing up, right? So let's do that. So let's just do, so we don't need this to be an attribute of the class. Well, actually, no, let's do this. So this is going to be our normal. We're building it, right? So let's call it self.norm is equal to P2 minus P1. That's the first thing we did. Our normal is going to be P2 minus P1, and that gets us this vector which extends from here all the way out here. And then we need to rotate this vector 90 degrees. So the way I've coded up in mine is I have this rotate vector. I have this rotate method which uses a standard rotation matrix, pretty hard coded in there, but that's how it works in mine. And so what we're going to do is we're going to do self.norm is equal to self.norm.rotate. And then I believe, yeah, so it's the angle in radians, which is going to be math.pi divided by 2. Except that gives us technically gives us a counterclockwise rotation, except our coordinate system is flipped because because the y0 is at the top of the screen in this library. So we're just going to do -1 times that. Not super important. You can figure out as you go. Figure out which way is the correct way to rotate it. But great, we've rotated it now. Now I have this really long vector here. We want to normalize it. It's crucial that this one is normalized. So let's go ahead and normalize it, and then we're almost done. We're just going to do self.norm equals normalize self.norm. And then these would just be your, whatever your math library has functions for normalizing it. And normalizing a vector, again, just dividing it by its length. So great, now we have our 2 vectors here, or 3 vectors actually. Great. Now we actually have to use this. So what we need to do is we need to make some sort of function that collides our ball. Our ball has a radius, a position, and a velocity. Make some function that collides our ball and updates the position. I'm going to go ahead and do this in main. I'm just going to create a function, and this is going to be collide. And then so it's going to take 2 parameters. It's going to take the wall, and it's going to take the ball. And what do we need to do? The first thing that we need to do from the math, let's go ahead and duplicate this and then start over. So we need to take the dot product. So what we have to do, we extend a vector from P1 up to the center of the ball. P1, and then this is the center. And then we take the dot product of that with the center vec1, with this vector, right? And we do the same thing on the other side. We extend this vector, and then we take the dot product with that. So, and we can store those. So let's call this dot one. Dot one is equal to, well, actually first we need to get that, we need to extend this vector. So let's call this v, I'm gonna call it vt. It's called, it'll be like vec test, right? Or yeah, we'll call it vec test one. I'm not gonna write that out with my mouse, but vec test one, vec test two. And so vec test one is equal to the center of the ball minus P1. And so, hang on, let me just see. So the center of the ball is pos for me. So we can do ball dot pos minus wall dot, is it P1? Yeah, minus wall dot P1, boom. And then we'll do the same thing, vec test 2 is equal to ball dot pos minus wall dot P2. And then we'll do vec dot 1. So then we need to store the dot product. So we're going to take the dot product of P1 and vec test 1, and we need to see if that's greater than 0. Same thing for this one. So we'll do vec dot 1 equals, how do they call it here? Dot equals dot, and then it's going to be wall dot center vec 1, comma comma vec test 1. There we go. And we do vec dot 2 equals dot wall dot center vec 2 vec test 2. Great. Now we need to check if these are greater than 0. If vec dot, oh wait, we're in Python right now. Vec test 1 vec dot 1 is greater than 0, and vec dot 1 and vec dot 2 is greater than 0, then let's just add some confirmation. Let's see. Can we do print like that in Python? Yeah. Print inside the box. Now let's go ahead and run our program and see. Oh, well, it would help if we were colliding, right? So let's update the ball, and then we're gonna do collide my ball, and or is it my wall, my ball? My wall, my ball. Boom. Let's see if this runs. And it doesn't compile. Vec2 is not defined. Hold on, I think we might be back in a minute. I'm going to debug my code. All right, and we're back. There was a slight error on my part where I was having the dot product return a vector, but the dot product actually just returns a scalar, so we're good. And as you can see, we've got some inside the boxes here printing out in our console. Let's go ahead and move this. So now when we run it, we'll see that it's printing inside the box. It's continuously printing because it is inside the box right now. But as you can see, it got a little off screen now, and it's outside the box. Let's see if we can move the ball to make it a little bit more clear. So if we start the ball off at a position, is this a good one? Yeah, so see, it's outside the box right now, and then as soon as it enters there, boom, we're getting our console printouts here. So this looks like it's working successfully. So now we need to move on to the next part of the collision algorithm. So the next part, if you remember, is we're going to be taking, okay, let's get out the paper here. We're going to be taking the dot product of, we're going to extend a vector from the center of the wall to the center of the circle. We're going to take that dot product with the, we're going to take the dot product of that vector with the normal. So a little more clear here. Let's say our ball's off to the side. We have our normal vector. We're going to extend a vector. This is wall.center, this is ball.center. We are going to extend this vector here and then take this dot product. And it's really important that the normal of the wall is normalized. It's a unit vector. I can't stress that enough, because what we're going to do is we're going to take the dot product of this so that's going to project this vector onto that, and it's going to get us this scalar here, which tells us how far along the normal of the wall the center of the ball is. And then we're just going to check if that's less than the radius. And if it's less than the radius, then we know the ball is colliding with the line. All right, so let's go ahead and implement this. So what we're going to do here is first, let's just modify this code a bit. So actually, no, we'll just keep doing it this way. So what we got to do is we are going to now, let's separate this code. So this is the first test, and then now we're going to separate this. This is the second test starting here. So the second test, what we do is we take we extend a vector, and so let's just call this center test vec is equal to, and then this is the vector that we're extending from the center of the wall up to the center of the ball. And so this is going to be ball.center minus wall.center, which is going to be ball.pause minus wall.center. There we go. Now we got the center test vec. And now what we got to do is center dot. We're going to take the dot product of this vector with the normal of the wall. So the center dot is going to be dot of wall.norm, comma, and it's wall.norm, right? It's wall.norm. Yeah, it's going to be wall.norm, comma, center test vec. Yep. There we go. And now we just need to add another, condition to our if statement here. It says if vec dot, so if these two are greater than 0 and this is greater than 0 and this value is, and center dot is less than the radius of the ball, which is going to be ball dot radius, I think. Let's check that here. Yep, if it's less than ball dot radius, then we're going to print inside the box. Now let's go ahead and see if this is updated here. So boom, and we're inside the box. So as you can see, we're falling, and then boom, it says inside the box. Notice that it says inside the box when we're all the way down here, even though we're not inside the box at that point. We're not colliding. And that's because this is, we said if center dot is less than the ball dot radius. So let's say that we're doing this diagram here and the ball is all the way down here. This dot product of here, from here to here of this vector is a negative number. So it's like negative, it might be -3 times radius, right? But it's less than the radius. So we actually sort of want to collapse this into just being this zone right here. The way we can do that is by taking the absolute value of the center dot. And so this would be, I think it's this. Let's see if that runs. Yep. And then we're falling and we're inside the box. Oh, it crashed. There is no, hang on, I'll be right back. I'm going to figure out what the absolute value is in Python. All right, turns out it's just ABS. Let's go ahead and fix that and see if that works. And here we are. We're colliding for a brief moment and then it stops. So I believe this is the correct behavior that we want. So let's go ahead and change this. This is just going to be colliding. And so boom, we're falling, boom, and it's colliding. All right, that looks pretty good. Let's go ahead and let's move our ball over a little bit. And I've got an idea. So boom. And let's go ahead and, so now we're just going to have this, instead of printing that it's colliding, we're going to have it return true if it's colliding, and then else return false. So if the ball is colliding, we're going to return true. Now let's go over into our function here and into our main loop here, and then what we're going to do is we're going to say if there's a collision, then how about we just stop. There's probably a way to stop a Pygame loop. All right, there is a way, and it's just setting the flag that I made for the loop here. I didn't have to look too far for that one. So, what did I do wrong here? Oh, there needs to be a semicolon. There needs to be a colon there. So the program's going to stop when it collides. Boom. You see that? Let's get that one more time. As you can see, boom, instantly as soon as it hits the line, we've made a collision. This is looking pretty good so far. This is looking pretty good. But this is not exactly the right way to handle it. You can't just quit the program every time something collides. So let's go ahead and add a little bit of collision resolution to this algorithm. Alright, so now we're going to add our collision resolution. And if you remember from the last video, I went over a method that we can use to resolve this collision. So let's go ahead and take a look at what we've got here. So if the ball is colliding, right, we have our wall and our ball right here. So when we take the dot product of this vector with normal, right, we get this length, which is along here. And so if we just slide that over here, and then so this is going to be our dot. We slide this over here, and we need to translate this ball up by this length right here, which we're going to call dr. And if you remember the observation in the last video, this distance from the center of the ball to the edge here, this is the radius. So we know radius is equal to dot plus dr. Dot plus dr, and so we know dr is equal to radius minus dot. Dr is equal to radius minus dot. So let's go ahead and then what we're going to do is we're going to translate the circle by dr times the normal vector. And again, this is important that the normal vector is a unit vector here, otherwise we're going to translate by the wrong amount. So let's just go ahead and implement this and see how it looks. So in our collide function is now going to be, instead of just returning true here, we're going to do collision resolution. This is where we're going to resolve the collision here. So now what we have to do is we're going to create our dr. So if we look here, we're going to do dr is equal to radius minus dot. So we're going to get our dr, and our dr is going to be equal to ball dot radius minus center dot, which is what we call it in code. And so dr is equal to ball dot radius minus center dot. And then we're just going to translate the ball. So ball dot pos is equal to ball dot pos plus dr times wall dot norm. And let's see how this works out. Actually, I think it has to be the other way around because of the operator overloading in Python. But let's see how this works. Oh, and we should probably not have it stop the program when it collides. So let's run it and let's see what happens. There we go. That's looking pretty good. The ball nestles itself up against that wall there, and it just sort of slides right off. Let's go and let's watch that again. Yeah, that's looking pretty good. Now notice that there are some problems with it. So it goes down here and then it sort of falls right through and it clips a little bit through right here. This is actually not a problem if we added another wall that went down this way. And maybe I'll demonstrate that at the end of this video, but that's pretty much the whole collision resolution that we have going on here. And the reason that it's jittery is we also need to take into account the time here. So in order to or perhaps we could look ahead into the next position of the ball by looking at its velocity, but there are ways to get it to be smoother. But this is just a pretty simple collision detection algorithm. And I think that that's going to be it for the video. This is just a post-recording addendum to this video. And one way we can improve this algorithm is by, rather than looking at the ball's current position, we can actually look ahead into its next position by finding the next position by adding the position plus the velocity times the change in times into the last frame. Here my change in time is a constant, but change in time in your frame, that should be something you're handling in your game engine, game loop stuff. So yeah, that's just a way you can improve it. So thanks for watching, and I'll see you in the next one.